right, so let's take a look at our new set of notes for sampling distribution. So our goal for these notes are to define a sampling distribution and to define what an unbiased estimator are. Now this unit doesn't have a lot of practical applications, but it also has a lot of practical applications. So what we're going to be talking about in this unit is kind of the basis for everything we are going to be doing for the remainder of the year. So the concept here is really, really important. So let's take a look at some vocab review, starting with a population distribution. So a population distribution is going to be a graph made up of all of the values of a variable which we would observe if we were conducting a census of all members in the population. Basically, if we plotted every single data point from every single person, that would be our population distribution, right? Now the issue with that is a lot of times a census is not going to be possible to obtain, so our population distribution most of the time would be like a theoretical density curve, like a normal distribution or a binomial or geometric distribution. So let's take a look at a population together. Here we have a list of years of experience for each teacher in the Lake Braddock Math Department. This needs to be updated, but more or less this is what we've got. Okay. Now our years of experience is going to be some quantitative variable. So how could we display this data? There are 4 different ways. Think about it. Well, the first way we could display it, and these are not in any particular order, is by a box plot. We could also make a stem plot, we can make a dot plot, or we can make a histogram. Okay. Since we know the data from all of the teachers, what I will make is a population distribution using one of these graphs. So since I have the data from every teacher, I could make a histogram, and that would be an actual population distribution, right? And here that is. Okay. So we've got our years of experience on that's our x-axis with the frequency on the y-axis. Right. Again, this is a population distribution. So every one frequency here represents one teacher within the population. Once again, trying to take a census can be difficult, it can be costly. So instead, let's simulate taking a sample to estimate the median years of teaching experience within the math department. All right, so I number each of the teachers from 1 to 20. Then I'm going to take a random sample of 3 teachers. And let's say I randomly select teacher number 8, teacher number 14, and teacher number 17. Cool. So we'll take the median of this sample because I'm trying to find the median age or the median experience for our Lake Braddock teachers. So that's going to be 5. Okay. Now 5 is something we call a statistic. And what a statistic is one of our center or spread measurements from a sample. A parameter, on the other hand, is the value from the entire population. So it's the median age of all of the teachers. So if I took my census and I got the median for all of the teachers, that would be considered a parameter. Whereas the median of my sample is considered a statistic. So, is this statistic the same as our value from our entire population? Maybe it is. Maybe it's not. We don't know. So let's take another sample. All right, now we sample teacher number 2, teacher number 13, and teacher number 15. We find that the median is 12. How is this statistic, or why is this statistic different from the median of 1? In number 1 we had 5, now we have 12. Those are really far off. Well, if you remember from Unit 3, that's a random sampling error. This is some variation due to chance, and it's because we have such a small sample size. But what if I keep taking more and more samples? Well, I'm going to have some variation, right? Okay. So how many possible, well, what if I wanted to take every single possible group of 3 teachers, so sample every group of 3 different teachers, and take the median from all of those groups? How many different ways could I get 3 people from this group? Well, to do this, we are going to do a combination, right? And the formula that we can use for that is 20 factorial over 3 factorial times 20 minus 3 factorial. And again, factorial means, well, 3 factorial would mean 3 times 2 times 1. 20 factorial would be 20 times 19 times 18 times 17 times 16 times 15 times 14, etc., etc., etc. Okay? And we would find that there would be 1,140 different combinations of 3 teachers that I could get from the 20 teachers that I am sampling from. So again, if we took me, Miss K, and Miss Kim, if we took me, Miss K, Miss Fava, me, Miss K, Miss Berge, me, Miss K, Miss Crode, and we did that in every single possible group of 3 individuals, there would be 1,140 different choices. Well, again, if I take every possible combination of 3 individuals and recorded the median for all those groups of 3, make sure you understand what I'm about to show you here, and I made a histogram of every single possible combination of 3 individuals, this is what it would look like, right? And this is called a sampling distribution. So I'm going to go back. Sorry. Our population distribution. What's being plotted here? Well, these are different teachers' ages. One teacher, right? One teacher's age. One teacher's age. Each one of these frequencies represents one teacher's age. When we go back to here, this is the median from 3 teachers. So here are all the medians from 3 teachers. So each frequency or each value is a median of 3 individuals, not a single person's age. That is what a sampling distribution is. We are no longer plotting individuals, we are plotting statistics from a group of individuals. If you can understand that concept, you are 90% of the way to understanding the most important concept in this unit. Right? So take a moment and think about what I just said. A population distribution plots each individual. A sampling distribution plots every single possible statistic from groups of a certain size. In this case, it would be all of the possible medians from every sample of 3 people, of 3 teachers. Here's that in words written out. So when we take every possible sample of the same size from a population and plot the statistic for each of those samples, we take every possible group of 3 teachers, find the medians for all of those groups, and we plot the medians. Now, from a sampling distribution, we can determine if we have something called an unbiased estimator. Right? And what an unbiased estimator means, or if we know that we have an unbiased estimator, it means that I could use a sample from the population to then estimate what the true parameter is for that population. So if something is considered an unbiased estimator, that means the statistic can be used to try to determine what the parameter is. Again, statistic is the value for the sample, parameter is the value for the population. So what is an unbiased estimator? Okay. Well, to determine if something is an unbiased estimator, we would take the mean of the sampling distribution, and that should be the same as the population parameter. So is median an unbiased estimator? Well, let's take the average of that sampling distribution that I created. Remember, these are all medians being plotted, And if I take the average of all possible medians from group of 3 teachers, that would be 13.43. Well, the actual median years of experience for the Lake Braddock Math Department is 13 years. These two are very, very close to each other. Therefore, right, the mean is very, very close to the actual median for the population. Therefore, median is an unbiased estimator. And if a median is an unbiased estimator for ages of teachers, that means it's an unbiased estimator for any population. Right? So, take a moment. You're going to take an index card, or take the index card that hopefully you all got at the beginning of class. Write your name, write your height in inches, okay? And then we'll have you go around and select 4 different cards, record the names and heights of the 4 chosen students. And based on your sample, you're going to calculate 2 statistics, the mean and the range, right? You can go ahead and make a dot plot of that data on the board. So plot your values on the board, and I'll give you a moment to pause and do that. Now, the big concepts is the mean. So when you take the average of those values on your dot plot, is the mean an unbiased estimator? Well, yeah, the center of that sampling distribution that you made. Now, technically, you don't have an official sampling distribution because you don't have every possible group of 4 students, but your values should have been pretty close to the actual mean height of the class. Is your range an unbiased estimator? Well, no. Your value, the average of that sampling distribution, should be quite a bit off from the actual range in heights of individuals. So since the mean is not since the mean is an unbiased estimator for your heights, that means that the mean is actually going to be an unbiased estimator for any population. And since the range was not an unbiased estimator for your heights, that means that the range is not a unbiased estimator for any population. So we can use a sample mean to estimate a population mean, but we cannot use a sample range to estimate a population range. So let's take a look at some other data that I picked up from my 5th period class last year. Okay. So here's the data that I have from the different students, for 25 students. All right, let's create a probability distribution for this. Now, political party is a categorical variable, so we could use a pie chart or a bar graph for this, and then we're going to make a bar graph. So the proportion of Democrats in that class was 44%. The proportion of individuals who identified themselves as Republicans is 32%. We have about between 4 and 8%, almost 8%, identifying themselves as independent, and about 12% identifying themselves as other, some other political party. Take a moment and take a sample size of size 5 using your random number table. Okay. Or you can use a graphing calculator. And this should be a p-hat. Sorry about the symbol. I'll do my best to include the correct symbol in the notes. But p-hat is the proportion of students who identified themselves as Republicans. So take a random sample of 5 students from here, determine the proportion of those 5 students that are Republican. Same thing for size 10, same thing for size 15. When you're done with that, we are going to plot your values on the board. So take a moment, plot your values on the board, and take a look at your shape, center, and spread for that data. Do the same thing for sample size 10, and the same thing for sample size 15. So our true population parameter, okay, was 36%. Now, as we take a larger and larger sample size, oftentimes what we will see for proportions, for our sampling distribution of proportions, is that it becomes more symmetric and closer to actually being normal. And you'll notice that, hopefully, you notice that yourself. Our value gets closer and closer to our center. However, our center gets closer and closer to our actual value. Right. And our spread also decreases as sample size increases. Those are some really, really important concepts there. As we increase our sample size, our distribution of every possible proportion, okay, out of groups of 5, 10, and 15 gets closer and closer to being normal. We have less variability, so our spread decreases as we increase our sample size. So p-hat, proportions, or sample proportions, is another unbiased estimator. Okay? The center of a sampling distribution of p-hat is going to be the same as the true population parameter. And that's going to actually be true no matter what sample size we take. But as sample size increases, the shape of our sampling distribution becomes approximately normal, and our variability goes down. Really, really important concepts here. I'm going to repeat that. So p-hat, a sample proportion, can be used to estimate what the actual proportion of the entire population is. Okay. When we increase our sample size, that means that the shape of our sampling distribution gets closer and closer to being normal, and the variability of those proportions will decrease. So we have a lot of values close to the mean, and as our sample size increases, there's not going to be a lot of variation away from that. Right? Think about how powerful that first, as we increase sample size, how powerful that is. If we have an approximately normal curve, there's a lot of things we can do with that. Well, that's going to be our notes for our first class today. We're going to do a little bit more of an exploration of sample proportions in our next class. Have a wonderful day and good luck with all your work.